I am teaching astrophysics this semester. So you may see some astrophysics videos. Maybe that's good, maybe that's bad, but here we go. So this is a question I asked in class. This is introductory level astrophysics. It's nothing crazy. We're just doing basic gravity stuff right now. And I had the question. Here's the question. Suppose I have the Earth and I launch an object this way, straight away from the Earth with an initial velocity of 7,000 meters per second. And it's going to go up, and it's going to come back down. And then I launch it at a 45-degree angle this way, and it's going to go not straight up, right? It's going to curve, but it's going to reach some maximum height away from the Earth. So which one's going to get further away from the Earth before coming back down? That's the question. Both those values are less than the escape velocity of Earth. You should know that. Now, what if I instead, part two, what about the escape velocity? If the escape velocity, which of those two objects will have a greater escape velocity? A, launched straight away, or B, launched that way? So in order to solve this problem, I'm going to model the motion of an object near the surface of the Earth with Python. And we're going to do it numerically first. And then we're going to come back and we're going to do it the real way. So maybe it'll be a long video, maybe it won't. This is a review. I've done many gravitational orbital problems before, but it never hurts to do it again. So let's just start off from scratch here. How do we model the motion of that thing? Because the first thing is that if I have the Earth right here, and then I have my object right there, and this is my origin. I don't even have to put it at the origin. Okay. So I have this vector. I'm going to call this RE. I have this vector. It's a ball. Okay. So I'm going to call this RB. And then I know I have a gravitational force. I'll just write that as F right there on that object. And the problem is that if this object is moving any significant way, that gravitational force changes in both direction and magnitude. So the first thing is, how do we calculate that gravitational force? Yes, I'm completely starting from scratch here. So this should be a great, you can just jump in and do this video. You don't have to have all my other 8,000 videos that I've posted. So the first thing is this, we're going to use this gravitational force. F is G. I'm going to call that capital M the mass of the Earth, lowercase m the mass of the object, over r squared. That's where you'd see it in the books. Okay, so here G is 6.67 times 10 to the negative 11th, and it's got units, but we don't have to worry about that. That's a bad equation. If I'm writing that and you're like, haha, he already messed up. Well, that's fine, because I did that on purpose. Because this is a scalar equation, and it's not going to help us model the vector force on this thing. So that's the first thing we need to do, is to write this as a scalar, a vector equation. So it looks like this as a vector. Negative G mass over the magnitude of r squared r hat. So here r is the vector from the center of the Earth to the thing right there. That's the vector r. So we can find r as r, the final position, which is r ball, minus the initial position, which is r Earth. So we need to find that, right? Now, if the Earth was at the center, at the origin, then it would just be the radius, the position, not the radius, the position of the ball would be r. Okay, but I'm trying to be this generic so we can use this for later things, and we will. But that's that r right there. I'm going to need to find the magnitude of that vector, and then I need to find the unit vector. So remember, the unit vector r hat is the vector r divided by the magnitude of r. So I can find that gravitational force on my mass. But what do I do with it? What do I do with the gravitational force? Well, here's where we can use the momentum principle. This says that the net force on an object is the rate of change of momentum. Now, momentum, in this case, we can define as mass times velocity. And you may say, well, you could just do a mass times acceleration. You could, but I like this way better. And this is my video, so I'm going to do it that way. Now, this is really tough, right? Because how do I find the trajectory of this thing or anything about this? Because that force depends on position, and the change of position depends on the momentum, which is changing too. So it's a tough problem. there are ways to solve this. There's the two-body problem, right? You can reduce this to a one-dimensional problem and it's solvable. You can do that. We do that in classical mechanics. Well, we're not going to do that, okay? Instead, I want to model this by breaking things into short time intervals. So let's just put this so we have enough room. So I have this, the gravitational force, negative g m r hat over the magnitude of r squared. And then I have the momentum principle, F net. This is only force is that one. I'm going to write this as delta P over delta T. So in a short time interval, let's say delta T equals 5 seconds. Okay, so if I'm talking about something moving 7,000 meters per second in 5 seconds, it's going to move pretty far, but we're talking about distances on the size of the Earth. So that might be too big. Let's put 1 second. In 1 second, it moves 7,000 meters, yes. But it's not that far compared to the size of the Earth. Probably should be a little bit smaller. But let's just proceed. So if delta t is 1 second, I can say, write this as the following. Let me draw another picture right here. So suppose my ball is right here, and it's moving this way with the momentum p1. And then a little bit later, it's going to be over here with momentum p2. And that's my short time interval. So F net is p2 minus p1 over delta t. That's the same thing, right? Delta p, delta t. Now I can solve this for p2. P2 is p1 plus f delta t. That's important. Let's put a box around it. Now I can use the definition of average velocity to find the change in position. Average velocity over that time interval is delta r, this is rb, rb over delta t. And this is equal to p2 over m. We're going to say that's equal to p2 over m. So p2 is the momentum at the end of the time interval. So we're looking at trying to find out where it moved to, and we're starting with that initial momentum. We're finding that final momentum, and we're using that final momentum as though it was traveling at that momentum the whole time, which it's not. Okay, I know that. It's fine. It's fine. So this is going to be equal to RB2 minus RB1 over delta t. So I can solve for this, and I get RB2, the final position, is RB1 plus P2 over m delta t. So that's it. That's all we have to do. I now know where is the object after 1 second, how fast is the object moving after 1 second. Now for the next second, I just do it again. Right now over here, I'm going to move, starting with that as my initial velocity, finding the new momentum, finding the new position. So here's my steps. Number 1, calculate the force. Number 2, update the momentum. Number 3, update the position. And in WebVPython, this is actually not too terrible of a thing to do. So let's just jump into WebVPython. I'm going to put my Earth. I'm going to put it at the origin just because it looks a little bit better. And I'm going to put my mass over here on the side of it. And it's going to launch this way with the velocity of 7,000 meters per second. And we're going to model the motion. And then we're going to put another ball. So I'm going to do 2 balls. I'm going to do 1 ball at a time. But let's put 1 ball there, and then we'll launch another ball right here with the same velocity but at an angle and see what happens. It's going to be fun. Switching over to Python. Here we are at Python. Okay. So WebVPython. My phone's ringing, and that kind of annoys me, but I'm just going to let it ring. We can just carry on, right? Okay. So I already have my values in here for. It is really annoying. I can just go pause it. It hung up. Okay. So I have my values for the radius of the Earth, the mass of the Earth, and the gravitational constant g. Let's go ahead and make the Earth. That's a little bit bigger. So the Earth is an object of a sphere. Its position is going to be at the origin. So we have these three-dimensional objects in WebVPython that allow us to make 3D things, and it's pretty awesome. The radius is going to be equal to r. So you already put it in there. And then texture equals textures dot earth. Run. Oh my gosh. Let me go turn this off. You know, this is my no editing philosophy. Don't edit videos. Hopefully that didn't bother you too much. I'm sorry about that. But you get to look at the Earth. And that's a 3D Earth, right? It's 3D. Okay, let's make it. There's one other thing I like to do, comma. I like to put the shininess. You don't have to do this. Is 0. It makes it not so shiny. Now, this is not the right way because there's more than one light source here. So you can fix that and make it better if you want to have a video on that. But don't worry about that. So there's my Earth. Now let's make my ball. I'm going to call this B1 because we're going to get 2. It's also a sphere. I'm going to put it on the positive x-axis. So the position is going to be the vector r0, 0. The radius, I'm not going to make it a real ball. I'm going to make it big enough. So say r over 20, color equals color dot yellow. Make trail equals true. So this means it will leave behind a trail when it moves around. Okay, so where's my ball? Okay, you can't quite see it because it's right there. It's on the. So I'm kind of zoomed out a little bit, so you can't really see. But there it is in the middle of the Indian Ocean, and that's just where it is. We could change it if we want to, but it doesn't really matter. Okay. Now a couple other things I need. I need my mass of the ball. I'm going to call this B1.m, which you don't have to do. 1 kilogram. The mass doesn't matter, so I'm just going to put it at 1. V0 is my magnitude of the initial velocity. It's 7,000. I picked that. So now I need the initial momentum. B1.p is going to be B1.m times V0 times vector 1, 0, 0. So now it's going to be initial momentum in the x direction. What else do I need? I need the time. I need the time step. I said I would do 1 second. And now let's run this for while t is less than 1,000 seconds. I don't even know how long I have to run it, but I want to go all the way up and come back, not all the way down. I want it to just get to the highest point. So the next thing when we make an animation, we need to include a rate statement. So this says how many calculations per second. So I'm going to run it at 100 calculations per second. So this, it's not going to run in real time. So just so you know. Now the next thing I'm going to do is to calculate the vector from the Earth to ball 1. You don't have to do this because the Earth's at the origin, but I'm going to call this R1. It's going to be equal to B1.pos, that's the vector position of the ball, minus Earth.pos, the vector position of the Earth. Now I can calculate the force. I'm going to call it F1. Again, remember, I have 2 forces I'm going to be doing here. Negative g times m times b1.m times norm r1. So norm is a built-in function in WebVPython that calculates a unit vector in the direction of r. So that's my r1 hat. So that's kind of cool. Divide by mag. Again, mag is a built-in function that returns the magnitude of the vector r1. I need to square that. Square in Python is star star 2. Okay, next, I'm looking at my board over here. I calculate the force. The next steps, update the momentum. B1.p plus F1 times dt. So a couple things. Just a reminder, that's not an algebraic equal sign. That's a make equal to sign. So I'm just changing the value of that variable here. It's not an algebraic equation. This is not minus F1 because F1's a vector, right? F1's in the negative r hat direction, but it's not a negative vector. Now I can update the position, B1.pos plus b1.p times dt divided by b1.m. Update time, t equals t plus dt. That's it. That's not so bad of a program, and we're going to get a lot for our money, right? Because one, it's a free program, and two, we get something really cool out of this. Let's run this. There's my ball. See, it's going up. I think I need to run this faster. Okay, so let's run this at 300. Okay, it's going to go up. And see, it started to come back down. I think it did. Let's see. Let's run it for a little bit longer, see if we can see it going down. It's going up. I don't think it is coming back down. Okay, let's run it for even longer. Let's just make sure we get it. 2,500 and this increases to 500 because that's just awkward waiting there for a whole second. There it goes. Okay, up. And then back down. Okay, so now it's coming back down. So it did get to its highest point. And we can print that out and find that later, but it doesn't really matter at this point. I just want to focus on animating it. Now what I want to do is to do the same thing at a second ball, but launch at a 45-degree angle. So let's do that. So I'm just going to go down here. Let's just add my second ball right here. B2 equals sphere. Position equals same thing, vector R00. Radius equals R over 20. Color equals color.cyan, different color. Make trail equals true. And then I need a mass, b2.m equals 1. I need the momentum. So let's say theta is pi over 4. I'm just going to write it that way. And then b2.p equals b2.m times v0 times. Now I want it to go down, just like I have in my picture. So the x component is going to be vector cosine theta. And the y component is going to be negative sine theta. And that's 0. Okay, great. Now down here, I need to calculate. I'm going to just, let's just do R2 is B2.pos minus Earth.pos. I can type pretty fast. F2, I'm going to copy that. F2, ddent, 2, you gotta, if you don't say it, doesn't work, 2. And then down here, I can type this one, B2.p equals B2.p plus F2 times dt, dt, and then this one, I'll just retype it. B2.pos, pos is B2.pos plus B2.p times dt divided by B2.m, and let's run it. Excellent. So which one went higher? Let's go ahead and calculate the max height of this, and then I'm going to draw a ring around the whole thing so we can just make a comparison. But that'll give us a lot of the how do you calculate that stuff. So let's switch over here back to the board and let's do some physics. Okay, I want to calculate the height of the one that goes straight away. Where did I put my chalk? There it is. Okay, so I have the Earth, and I have my ball, and it has initial velocity v0. And it's going to go up here to final height. Okay, and let's call that height r2. So let's call this, I guess I should call r. I should call that v1, but I'm calling it v0. And let's call this r2. So this is initial position is capital R, the radius of the thing. So I'm going to use the system of the Earth plus ball. And now I'm dealing with a change in position, so that says, hey, use work energy. So work is the change in kinetic energy plus the change in potential energy. And if that's my system, I'd already started with initial velocity. There's no external forces, so the work done is 0. So that's good. So I can say 0 is going to be k2 minus k1 plus u2 minus u1. And remember, k is 1/2 mv squared. U is negative g m over r. And we can derive that later. I didn't derive that. And that's the potential with respect to infinity. But it doesn't matter because I put in the change in potential here. So 0 is going to be k2. If I launch this, I want to find out where it is at that highest point. The highest point is where it goes from moving this way to moving that way. So it had to stop. So at the highest point, k2 is going to be 0 minus 1/2 mv. I'm going to call it v0 squared, which is dumb, but you got to stick to your dumb choices. u2 is going to be this position, so it's going to be minus g m over r2, and then minus a negative, so plus g m over capital R. That's where it starts. And remember, I'm trying to solve for r2. So let's move this to the other side. I get g. The mass cancels. The little mass cancels. I told you it didn't matter. So I get g m over r2 is g m over r minus 1/2 v0 squared. And I can just solve this. I'm going to write this in a poor format, but I'm going to solve it anyway. R2 is going to be equal, so I'm going to divide by gm. So R2 is going to be 1 over R minus V0 squared over 2 GM. Yeah. Okay, so let's calculate that and then put a ring around the Earth of that radius so that we can see that. So that's going to be our R max for the one that's launched further away. So going back to Python, edit. Down here after the loop, I'm going to calculate that. R max, I'm going to call it. And it's right here what I said. 1 divided, is that right? Yeah. Yeah, I think that's right. Yeah, okay. 1 divided by, this looks weird, but, oh, I didn't even switch. You have no idea what I'm doing. There you go. 1 divided by 1 over R. 1 over R minus V0 squared divided by 2 times G times M. And whatever that is, I don't think, oh, that's capital, that should be capital M. Now I'm going to make my ring. So let's just, I'm not even going to give it a name. Ring, the position, so ring is an object in WebV Python. The position is going to be at the origin, vector 0, 0, 0. The radius is going to be R max. Now, the ring has an axis vector, right? Because you can orient it different ways. So I want it in the z direction. So the axis is going to be the vector 0, 0, 1. And then I need a thickness. Thickness equals, let's say, R over 40. Let's just see what happens. So here they go, launched up, and then it'll draw the ring at the end. Or not draw the ring, because there's an error. V0 is not VO. That was dumb on my part. Look at that, V0. Funny. Okay, you get to run it again. Here we go. And there's the ring. So you can see that that ring is the size for this mass that's launched straight up. This one didn't get as high. It's easier to see that. It did not get as high, okay? So you may think, well, hey, the work energy equation says that it doesn't really matter what direction you're going. It's a scalar equation. But if we go back over here to our board, if I take this and launch it this way, I can't draw like that. Okay, right here, it's not at a 0 velocity. It still has some velocity horizontal or parallel to the surface of the Earth. and so it doesn't get to zero velocity. So it has the same amount of energy. For this one though, K2 is not zero. Okay. Now let's go ahead and calculate the second question. So that's the first question was which one goes higher, the one launched straight away, because the other one doesn't get to a highest point of zero velocity. Okay. Now let's do the escape velocity. It's pretty easy, right? So escape velocity says the same thing. I'm going to launch it with an initial velocity 0, and it's going to go over here an infinite distance away with 0 velocity. So it's going to go all the way up. It's not going to come back. It's going to escape. So we're going to use the same equation right here, but we can just modify it. Yeah. So the only difference here is that we're going to start, that's the same. Our initial velocity, we're going to solve for the initial velocity, but here the final position is going to be infinity. So if I let r go to infinity, this whole thing goes to 0. So now I have 0 equals negative 1/2, the masses are already canceled, v0 squared plus gm over r. And then if I solve for v0, I get v0 squared equals 2 gm over r. v0, this is escape velocity, is equal to the square root of gm 2gm over r, the starting position. Okay. But will they both escape? So let's just run this and see what happens. Let's see if they get the same distance away. Now, it's kind of hard because we're not going to let them go to infinity because it's a code, right? So let's calculate the escape velocity, print it, and then give those two things the escape velocity. And I'm not going to delete the ring. I'm going to comment out the ring. Well, I can keep that there. You may want that. I can give you the whole code. You know I'm going to give you the code. So let's go ahead and calculate the escape velocity. V escape, it's going to be equal to the square root. I'm looking at my equation right there. 2 times g times m over r. And I have all those values, so that's that. So now I'm just going to say v0, let's just not that. Let's just comment out this, this, and put v escape. That's all we have to do, okay? Oh, and you didn't even see any of that. Look at that. That's the second time I didn't do that. Okay, so what did I do here? All I did was to type in v escape right there. I commented out the ring below. I commented out the v0, so now it's going to be set equal to that thing right there. And that's it. Let's run it and see what happens. Oh, let's do this for 5,500 seconds, and let's increase this to 1,000 frames per second. There they go. There they go. Now, of course, they're not going to escape, right? 'Cause I don't have it going on forever. But you'll see that once you get far enough away, it doesn't really matter which direction you're going. And the velocity is going to be 0 in either case. So there is no directional dependency on the escape velocity. And in fact, let's do this. You can make a graph and plot this, but I'm not going to do that. I'm going to change this to pi over 2. So one's going to be launched parallel to the surface of the Earth. And let's see what happens. Zoom in. And they're both going to still escape. It doesn't matter. The direction does not matter for escape velocity because you're assuming it's going to get an infinite distance away with a 0 velocity. Now, it may take a different time to get there, if you could even do that. But the escape velocity does not depend on direction. Maximum height, if it comes back down, does depend on the direction. But the most important thing here is how do we model motion with gravity? And that's how. So we'll do graphs later, but that's your introduction to modeling things near an object like the Earth. Code down below. I'll talk to you later.